Good morning, everyone. My name is Johan Chrisnata, and today I'm going to talk about optimal reconstruction codes for deletion channels for the Non-Volatile Memory Workshop 2021. So this paper has been published in ISITA 2020, and the full version of the paper is uploaded in the archive with the same title. So for those of you who are interested to find the full version, you can just Google optimal reconstruction codes for deletion channels. Okay, so for this talk, I'm going to divide it into two sections. First, the introduction, namely the motivations of the problem and the definition of the problem, and also the past results and contributions. And for the second section, I'm going to talk about the general idea for lower bound, namely the notations and the definitions of some terms that I'm going to use, and also the general idea on how to find the lower bound. Okay, so the sequence reconstruction problem was introduced by Levenstein in 2001, in which a code word X is sent from a codebook C through some channel, and then the receiver or decoder receives multiple noisy reads from x1 tilde until xn tilde, instead of just one noisy read like the classical coding theory. And now the decoder or the receiver aims to reconstruct the original sequence X from these distinct noisy reads. And our goal is to construct a code that makes use or leverages on these multiple noisy reads so that it has better rate than a code that only makes use of one noisy read. Okay, so this problem has several applications in ultra-high density data storage, such as, for example, the DNS storage and also the restrict memories. And they provide users with multiple cheap and although maybe noisy reads. And in our companion paper, we propose a variant of the problem where we fix the number of noisy reads to be n, for example. And our goal is to design a codebook such that every code word can be uniquely reconstructed from any n distinct noisy reads. And in our companion paper, we propose a coding solution or code construction to leverage on these multiple reads to increase the information capacity or equivalently to reduce the number of redundant bits. So now the big question is, how large can this codebook be? Or what is the optimal rate or the minimum redundancy of this code? For this paper, we will focus on deletion channels only. That means we will only deal with deletion errors. To be more formal, we will define the sequence reconstruction problem as follows. So we consider an error ball function B to be from an input space X to an output space Y, and a code C to be a subset of the input space X. And our goal is to determine the read coverage of C, which is denoted by this phi CB, and is defined to be the size of the maximum intersection of the error balls between any two distinct code words in C. So it's the size of the maximum intersection of the deletion balls, in this case, between any two distinct code words. And Levenstein showed that 1 plus this quantity, phi CB, distinct noisy reads are sufficient to uniquely reconstruct the original sequence or the code word in C. So here's an example of if, let's say, we let B to be the error ball of single deletions only. So now if B is single deletion error, and we have 8 binary words of length 4 here on the left. So these error balls of these 8 code words are given on the right. For example, here 0101. If X is 0101, then the error ball has 4 words. The first word is obtained by deleting the first bit of 0. The second word is obtained by deleting the second bit of 1. The third word is obtained by deleting the third bit of 0. And the last word is obtained by deleting the last bit. So here in this case, if you look at the intersection of the deletion balls or the error balls of the bold words, these two words, it will be these two words in red, which are 101 and 010. In general, if we consider all 16 binary words of length 4, In general, it turns out that the read coverage or the maximum size or the size of the maximum intersection is 2. So it turns out to be 2. In other words, if we pick C to be all binary words of length 4, then that means 3 noisy reads are sufficient to uniquely reconstruct the original sequence. Now, if we pick the code C to be just 4 code words in red, and then it turns out that the intersection between any two error balls are empty. So in other words, the error balls are disjoint, and hence the read coverage of this code C is 0. That means one noisy read is now sufficient to reconstruct the original sequence. So if we look into this carefully, we will notice that these 4 words in red actually forms the VT code of length 4. So, and then we know that the VT code is known to be able to correct one deletion. That means it should be able to uniquely reconstruct just with one noisy read. Now, if we let C to grow, just now from VT code the size is 4, now we have more code words in our code. That means we have better rate. So now we have 6 code words in red, and the deletion balls are the one on the right. It turns out that the read coverage is 1. That means the maximum size of the intersection is 1. Hence now 2 noisy reads are necessary and also sufficient to reconstruct the original sequence. So this is the summary of the previous work. If let's say B is the error bar of single deletions only, then we have these 3 codes that we want to compare. First is all binary words of length n. So we just take all binary words of length n to be a code, or also the VT code known to be able to correct one deletion, and also this CSVT code, which is a code that we proposed in our companion paper by Kia et al. In 2020. So what's the difference between these 3 codes? The difference lies in the read coverage. So for the VT code, the read coverage is 0 because the intersection of the error ball has to be empty. And for all binary words of length n, the read coverage is 2. And it turns out that for the CSVT code, it's proven that the read coverage is 1. Hence, it requires just one more than the one more of the number of noisy reads than the read coverage. And this line here gives the redundancy of each of these 3 codes. So for the VT code, the redundancy is log n. All binary words of length n, that means it has no redundancy because we take everything. And the CSVT code is known to have redundancy of log n plus big O of 1. But now the question is, what is the optimal code that we can construct given that we have 1 noisy read, 2 noisy reads, or 3 noisy reads, for example? So for 1 noisy read, it was shown that it's to correct one deletion error, given that we only have access to 1 noisy read, we require log n redundancy. That means this VT code is already asymptotically optimal. And of course, if we are given access to 3 noisy reads, we can uniquely reconstruct everything, even if we take all binary words. So that means the minimum redundancy is just 0. But the question is, now if we are given access to only 2 noisy reads, what is the minimum redundancy? So is this CSVT code an optimal code already, or is there a better code than the CSVT code that can correct one deletion with 2 noisy reads? Through this paper, we answer this question, and the answer is this CSVT code turns out to be optimal asymptotically because the minimum redundancy required is at least log n plus big O of 1. So if we observe, actually from left to right, it requires more redundancy from 0 to log n to log n redundancy, but also from left to right, it requires less noisy reads. In other words, from 3 to 2 to 1 noisy read required to uniquely reconstruct the original code word. So our result can also be extended to T deletions. So for T deletions, we answer the question of what is the read coverage of the CSVT code for T deletions. So we also expect that the read coverage should be in between the read coverage of all binary words of length n and also between the VT code. And it turns out to be correct. So it's approximately half of the read coverage of all binary words of length n. And for example, if we plug in t to be equals to 2, so now the error ball is 2 deletions. Now we want to correct 2 deletions. If we take our code to be all binary words of length n, then we require 2n minus 4 plus 1 distinct noisy reads to uniquely reconstruct the original code word. But now with CSVT code, we only require n plus 1 distinct noisy reads, which is about half of the number of noisy reads if we take all binary words of length n. Of course, the redundancy also increased from 0 to log n and to log n. So this is the summary of the past results. For single deletion channel, we show that log n plus big O of 1 redundant bits are necessary to reconstruct a code word from 2 distinct noisy reads. And we also show that for T deletion channels, the read coverage is n to the power of t minus 1 plus big O of n to the power of t minus 2. Now we want to talk about the general idea on how to find these lower bounds actually. So first we define dx to be the error ball of x of exactly 1 deletion. And then we define Gn to be a graph whose vertices consists of all binary words of length n. And then we say that the two vertices x and y are adjacent if and only if their size of deletion balls is exactly 2. So here's an example that was shown in the previous few slides. These two words has intersection of deletion balls 011 and 001. Hence, the size is 2. So we put an H between these two words in G4 because they are adjacent. We also define two words x and y to be type A confusable if x and y can be written as a common prefix u, a common suffix v, and a middle part, A and A conjugate here, or A complement. So what is this A? A has to be an alternating sequence of length at least 2. Alternating sequence means it's a 2 periodic sequence, A1, A2, A1, A2, A1, A2, where A1 is not equals to A2. And A complement has to be the complement of A, of course. So here's an example. These two words, 0101 and 0011, are type A confusable words because it can be written as a common prefix 0, a common suffix 1, and the middle part here is 10, another one is 01. They are complement of each other, and they are alternating sequence of length at least 2. However, the second example are not type A confusable words because the middle part, this one is 1, another one is 0, they are of length 1 only. But we require in the definition to be type A confusable, the length has to be at least 2. And the third example are not type A confusable words as well, because the middle part are not alternating sequence. It's 0, 0, and 1, 1. We have a theorem in the paper that says that two words, to know whether two words have intersection of the deletion ball of size 2, we just need to look if they are type A confusable or not. So if they are type A, so the theorem says that two words are type A confusable if and only if the intersection of the deletion balls is of size 2. So for example, these two words, since they are type A confusable, as shown in the previous slide, it turns out that the intersection of the deletion ball is also of size 2. For the second example, since they are not type A confusable, so the size of the intersection of the deletion ball is not of size 2. And for the third example, since they are not type A confusable, so the intersection of the size, the size of the intersection of the deletion ball is also not 2. So our original problem is, if you remember, is to find a lower bound of the redundancy of a code C. Or in other words, we also want to find an upper bound of the rate. What is the upper bound of the optimal code C? Such that the read coverage is equal to 1 because we are only given access to 2 noisy reads. Right? So that means we want our code C to have read coverage of size 1. So for any code C, to satisfy that the read coverage is 1, we need to have two words in C to not be adjacent in Gn. Because if they are if there exist two words that are adjacent in Gn, if you remember the definition, they are adjacent if and only if the size of the intersection of the deletion ball is 2. So if the size of the intersection is 2, then the read coverage cannot be 1. In other words, C must form now an independent subset in the graph Gn. So now our problem transforms into finding an upper bound of the size of a code C, where C forms an independent subset in Gn. Next, we define a collection Q of clicks to be a click cover of G if every vertex in G is covered in some click, or in other words, belongs to some click in Q. And then we also have a theorem that says if Q is a click cover, then the size of any independent set is at most the size of Q. So now our problem transforms again into finding or constructing a click cover for Gn whose size forms an upper bound for any independent subset of any binary words of rank n, and thus also forms an upper bound for the size of any code C. So our objective is now to construct or to find a click cover for Gn that whose size later on will be the upper bound of the size of any code C. So since we want to have the best upper bound, in other words, we want to have our upper bound to be as small as possible. So our goal is to construct a click cover whose size is not very big. So we want our click cover of Gn to be as small as possible. So for the next slides, we are going to give you two methods. The first method is our first attempt of finding a click cover. And our second method is going to be better than the first method, which is the method that we put in our paper to find the click cover. So for example, if n equals to 12, this is the first method, is the length, so 12 is the length of the code. Now our objective is to find a click cover of G12 with the smallest possible number of clicks, right? Because we want to find the best upper bound. In general, for example, if n is equal to 2L and A is 0, 1 and B is 1, 0, then this set lambda, which consists of A to the power of L, which means we concatenate A L times, and BA to the power of L minus 1, B square A to the power of L minus 2, and so on until B to the power of L, we will see that this set lambda actually forms a click in Gn. Here's an example. If we have BA to the power of 5, if in this case n equals to 12, that means L is 6. That means it's 1, 0, which is B. And then we have 5 A's. And we compare it with B to the power of 4 A squared. That means we have 4 B's and 2 A's. They are type A confusable because the middle part, which is the red part, they are alternating sequence. They are complement of each other, and the length is at least 2. And thus, by our theorem, they are adjacent actually in G12. So that means any two of these, actually, we can observe that any two words in this set lambda are actually adjacent in G12 or in general Gn. So now we will consider two types of clicks. First is the group clicks, or this kind of click, which is the lambda. And also we have the singleton clicks, which are clicks of size 1, actually. So what are the singleton clicks? Well, for the first method, we said we define our singleton clicks to be just clicks that contain words that is not in lambda. So in this case, since lambda is of size 7 for L equals to 6, and then we have a total size of 4,090 clicks. So this doesn't look very good. So let's see our second method. We will use a little bit different approach, but we will use about the same idea as the first method. So now, given n, we look for some s that is smaller than n, and then we construct lambda based on the definition of the previous slide. But now lambda is a subset of binary words of length s, not of length n, such that any two words in lambda are adjacent in GS, not Gn. So for example, if n equals to 12, now, for example, let's say choose s to be equals to 4. And hence our set lambda is these three words, right? So these three, any two of these are adjacent in G4. But if you remember, our quest is actually to find cliques of length 12. So our idea is to, if let's say we have length 12, we partition 12 into 3 blocks of length 4, for example. And then we again consider two types of cliques. First is the group cliques, which are cliques of size at least 2, and singleton cliques, which are cliques of size 1. So what are these group cliques? So if S is 4, and lambda is given as such, we let lambda tilde to be just all binary words of length S, in this case, all binary words of length 4, that is not inside lambda. And then we define the group clique as follows. So the group clique is when there exists a block of lambda. So here, a clique of type 1 consists of 3 blocks of length 4, where the first block is taken to be words in lambda, the second block can be anything, and the third block can be any binary words of length 4. So for example, if we take y2 to be 0, 0, 0, 0, and y3 to be 1, 0, 1, 0, then clique of type 1 consists of these 3 words, where the first word, the first block of the first word is from the first word in lambda. And then it follows, and then the second block is y2, and then the third block is y3. The second word of this clique, the first block comes from the second word of lambda, and then follows by y2, follows by y3. The third word, the first block comes from the third word of lambda, and then it follows with y2, and then follows with y3 again. So we can actually observe that any two of these 3 words are actually adjacent in G12. So for clique of type 1, we have several choices for y2 and y3. In total, we have 2 to the power of 4 choices for y2, 2 to the power of 4 choices for y3. So in total, we have 2 to the power of 8 choices for both y2 and y3. And we can also see that all of these cliques are disjoint. For clique of type 2, now is the first block does not contain lambda, because if the first block contains some words in lambda, then it's already considered in the clique of type 1. So for the clique of type 2, we want so that the first block does not contain any word in lambda. The second block now consists of words in lambda. The third block can be any binary words of length 4. So now we have only 13 choices for the first block and 16 choices for the last block. Now for the clique of type 3, the first block is not from lambda. The second block is not from lambda. In other words, it has to be from lambda tilde. And the third block is now blocks from lambda. So now we have 13 choices for the first block and 13 choices for the second block. In total, we have 633 group cliques. Now we have to count the singleton cliques, which are cliques that is not included in the group cliques. In total, there are this many singleton cliques, and hence we have 2,830 cliques in total. This is significantly less compared to the first method of 4,090 cliques. So this idea can actually be generalized to any length n. So in general, if we partition the length n into blocks of length s, the total number of cliques is given by this. And now we want to minimize this. We set several parameters for s and l. So we set s to be 2l and l to be the ceiling of this function. We can show that n minus logarithm of the size of c, what is this quantity? N minus logarithm of size of c is the redundancy of the code c, because logarithm base 2 of the size of c is the rate of c, n minus the rate is the redundancy of the code c. So we can show that the redundancy of the code c is bounded below or lower bounded by log n minus 1 minus small o of 1 if we take epsilon tends towards 0. So that means the minimum redundancy required is actually log n plus or minus some constant. which means that our CSVD code is already asymptotically optimal. So that's how we prove that our CSVD code is asymptotically optimal to correct one deletion if you are given two noisy reads. So that's all for my presentation. So I put the references here just in case you want to see. And thank you so much for listening to my talk. I hope you enjoy the rest of the sessions for the NVMW. So thank you for your attention.